Hi everyone, this is Alex from Made Intuitive, and today I'll be explaining the formulas in the Topic 2 Functions SL and HL section of the IB Mathematics Analysis and Approaches formula booklet. The formulas I will be covering today are on the screen right now. Note that I will not be going over these formulas in the order they appear in the formula booklet, but will rather follow the orders which aids the explanation best. Anyhow, let's get started. The first formula we will look at today is the gradient formula for a straight line. The gradient is defined as the degree of steepness of a graph at any point, and on a straight line, this degree of steepness is constant for all points on the graph. So, we can find the gradient of a straight line by arbitrarily choosing any 2 points, which we will call x1, y1 and x2, y2, and dividing the difference along the y-axis, y2 minus y1, by the difference along the x-axis, x2 minus x1. So if we denote the gradient using m, we get the following formula. Now, to derive the equations of a straight line, let's revisit the fact that the gradient is constant for all points in a straight line. In other words, if a line passes by a point x1, y1, and we also know that the gradient of the line is m, then we know that any coordinate xy such that y minus y1 over x minus x1 equals m is on the line. If we multiply x minus x1 on both sides of the equation, we get the equation y minus y1 equals mx minus x1. Similarly, if we know the gradient as well as the y-intercept of the straight line, we can get a different, arguably more specific form for the equation of a straight line. If we again call the gradient of the line m and the y-intercept of the line 0c, we get that any coordinate xy such that y minus c over x minus 0 equals m is on the line. If we multiply x, then add c to both sides of the equation, we get the equation y equals mx plus c. Note that because we are able to see what the gradient and the y-intercept of the straight line is just by looking at the equation, this formula has the name gradient-intercept form of a line. Finally, let's explore another equation of a straight line, which is ax plus by plus d equals 0. If we rearrange this equation for y, subtracting ax and d, then dividing b on both sides, we get y equals negative a over b x minus d over b. So our equation reduced down to the gradient-intercept form of a line, except that instead of m, the gradient is negative a over b, and instead of c, the y-intercept is negative d over b. The point is, this shows us that the equation ax plus by plus d equals 0 is indeed an equation of a straight line. The next formula is used to find the solutions of a quadratic equation, widely known as the quadratic formula. A quadratic equation is an equation whose highest power term is to the power of 2. Namely, it is any equation that can be rearranged into the form ax squared plus bx plus c, where a cannot be 0. Note that when a is 0, ax squared plus bx plus c becomes a linear function, and the solution to the linear equation bx plus c equals 0 is simply x equals negative c over b. Back to the quadratic formula, we are going to begin by making the coefficient of x squared 1. We will do this by dividing both sides of the equation by a to get the following. Next, we are going to make the left-hand side into a perfect square so that we get x plus some constant squared equals some other constant. Such a form is desired, as we can then solve the equation through the following steps. So, we are going to work backwards and rearrange x plus k squared equals j to be of similar form as x squared plus b over ax plus c over a equals 0. Now, we can compare the x term and constant term in the following equations to get 2k equals b over a and k squared minus j equals c over a. From 2k equals b over a, we get k equals b over 2a, and from k squared minus j equals c over a, we get j equals k squared minus c over a, and now we can substitute k equals b over 2a to get j equals b squared minus 4ac over 4a squared. Therefore, we know that the quadratic equation we started with, which is ax squared plus bx plus c equals 0, is equivalent to x plus b over 2a squared equals b squared minus 4ac over 4a squared. This implies that x plus b over 2a is equal to plus minus square root b squared minus 4ac over 2a. If we subtract b over 2a from both sides of the equation, we get x equals b plus minus square root b squared minus 4ac over 2a. And using this, we can find the solutions of any quadratic equation. Next up is the formula for the discriminant of a quadratic equation. In general, the discriminant of a polynomial is a quantity that depends on the coefficients and tells us the properties of the roots without computing them. For a quadratic equation, the discriminant, which is denoted by the delta symbol, is equal to b squared minus 4ac, and it tells us the number of real unique solutions that the quadratic equation has. Let's see how. You may have noticed that b squared minus 4ac also appears in the part of the quadratic formula underneath the square root symbol. This is no coincidence. From the quadratic formula, we know that the solutions to a quadratic equation ax squared plus bx plus c equals 0 are negative b plus square root b squared minus 4ac over 2a and negative b minus square root b squared minus 4ac over 2a, which we will call x1 and x2 respectively. Now, when the discriminant of a general quadratic equation b squared minus 4ac is greater than 0, x1 and x2 will be real numbers and also not be equal to each other. This means that the quadratic equation will have two real unique solutions. Meanwhile, when the discriminant is equal to 0, x1 and x2 will still be real numbers, but they will both be equal to negative b over 2a. Therefore, the quadratic equation will only have one real unique solution. Finally, when the discriminant is less than 0, x1 and x2 involves taking the square root of a negative quantity, so they will not be real numbers. As a result, the quadratic equation will have no real unique solutions. This means that if we plot y equals ax squared plus bx plus c on a xy plane, the graph will intersect the x-axis, or alternatively y equals 0, at two different points when the discriminant is greater than 0, at a single point when the discriminant is equal to 0, and at no points when the discriminant is less than 0. The next formula tells us the axis of symmetry of the graph of a quadratic function. During our derivation of the quadratic formula, we found that x squared plus b over ax plus c over a equals x plus b over 2a squared minus b squared over 4a squared plus c over a. So, ax squared plus bx plus c, which is equal to a times x squared plus b over ax plus c over a, is equal to the following. In other words, if we let f of x be equal to ax squared plus bx plus c, we are actually letting f of x be equal to ax plus b over 2a squared minus b squared over 4a plus c. Now, let us evaluate f of x when x equals x1 minus b over 2a, where x1 is any real number. We get ax1 squared minus b squared over 4a plus c. Next, let us evaluate f of x when x equals negative x1 minus b over 2a. Since negative x1 squared is equal to x1 squared, we again get ax1 squared minus b squared over 4a plus c. Therefore, f of x1 minus b over 2a is equal to f of negative x1 minus b over 2a for all real x1. And this means that the function f of x equals ax squared plus bx plus c is symmetric about x equals negative b over 2a. The last formula we will look at today is about exponential and logarithmic functions. In the previous video, we saw why the conditions ax greater than 0 and a not equal to 1 are necessary, and also that the log cancels out when it is raised as a power to its base. If these don't ring a bell to you, go check out the video in the description. Anyhow, we know that a equals e to the power of log base e of a, where e is Euler's number, a very important constant in mathematics. Euler's number is so important that there is a special name for logarithms whose base is e. Logarithms with base e are called natural logarithms and are denoted as ln. So, e to the power of log base e of a is equal to e to the power of log a. If we raise both sides of the equation to the power of x, we get a to the power of x equals e to the power of log a to the power of x. Therefore, by exponent rules, we get a to the power of x equals e to the power of x log a. Next, since log cancels out when it is raised as a power to its base, we immediately get that a to the power of log base a of x equals x. Finally, from the relation between exponents and logarithms, the equation a to the power of x equals b is equivalent to the equation x equals log base a of b. If we substitute a to the power of x for b in the second equation, we get x equals log base a of a to the power of x. Therefore, log base a of a to the power of x is equal to x, which is also equal to a to the power of log base a of x. In the next video, I'll cover the formulas from the Topic 3 Geometry and Trigonometry SL and HL section. I hope that helped.